We are going to today continue our discussion and exploration of OpenMP. Last lecture, remember we saw that we can use OpenMP pragmas in C++ to turn a serial code into a parallel code by basically saying what parts of the code can be done in parallel. Remember, the code starts off in serial. There's just one thread of execution. Then when you hit pragma OMP parallel, as long as you have compiled with the OpenMP flags, it will then create or spawn as many threads as there are in either the machine or in the OMP num threads environment variable, and then it will do the remainder of that block that follows the same for every thread. We also saw how to make each thread do something different, either by using the OMP get thread num function or with the pragma OMP for, which can split up a for loop among different threads. Now that worked because in that for loop, every element, every iteration was independent and could be done independently. And that is exactly the point. You can't do something parallel if your iterations can't be done independently. So today we're going to look at a few cases where that is not exactly true. There are some dependencies, and yet we want to be able to parallelize our loops. So I've got the wrong slides here. Hold on a second. That's weird. There we go. So the first one we're going to look at is a thing called reductions. I'll explain what those are, but they're rather common. Here's a prototypical case of a reduction. I mentioned that x and y are two vectors. So they have elements xi and yi. Say there's a bunch of elements. And I want to sum them. I want to multiply element-wise each of those vectors, and then sum that up. That is the dot product of two vectors, right? That's just what that is. So this n here is x dot y, and that's what it is. So we're going to look at a serial implementation of this, so a regular implementation in C++, and then we'll try and use OpenMP. And then because we're interested both in timing and correctness, we're going to look at the answer, make sure that it's correct, and how long things are taking. So to do the timing, we've seen this little guy before. We have a TikTok library that can be used to create a timer. So the timer here is called TT, and by saying tick and tock, I can measure a subpart of the program. What are we doing here? We're going to do an n dot, so compute this dot product between two vectors, x and y, and the vectors are going to be 20 million elements long. Here they are, x and y. We're going to fill them with a number, so they're basically growing linearly from 0 to n-1. And we do that in particular in this case because one can compute what the dot product should be. The answer will be stored in the number n's, and this is the one. I'm not quite sure why nn is equal to n, but that's strange. In any case, that's the answer. We're going to compute the dot product inside the TikTok so we can see how long it took. We'll print out the answer and the exact answer to compare with it and how long it took. So that's the driver. Of course, the actual work is done in the n dot function that is here. So a serial n dot would have two arrays coming in, and then a loop from 0 to n-1, adding the product of xi and yi. And so this is the part that we really want to parallelize. You have a for loop. We think that's possible. So if you run it, and this is in the same repo that you could have cloned last time. So it's in /sinet/core/PHY1610, and I think /OpenMP then. So if you make this one, you get a dot product answer. You get the exact answer, which matches good. And this took 0.1 seconds to compute. So that's pretty good. Now, anytime you would really have a program that runs in 0.1 seconds, you shouldn't think of for a second to even parallelize it, because even that thinking about it is more wasteful than not doing it, right? So, but this is an example, and we're going to see if we can speed this up using more than a single core. So the loop seems very parallelizable. Every one of these multiplications here is independent for every value of I, so that should be doable. And we want to add it to the same variable tot so that they all add up. So that has to be a shared variable. So the first instance, or the first try to parallelize this, could just be putting in front of this for loop pragma OpenMP parallel 4. So what that did is parallel creates the threads, and 4 divides the I iterations among the threads. So say that there were 16 threads, then whatever n over 16 is, that is roughly how much every thread gets. We like our default none, so we have to have some shared variables. Tot has to be shared because they all have to be writing to the same variable. If it were private, we would not get the answer out at the end because all the private variables disappear when the threads are gone. And x and y have to be accessible. I have a feeling n should probably also be shared, but that might be automatic depending on your compiler. Okay, so this is a try. We're doing things in parallel now. So we're going to make this one. If you type make OpenMP num or n.race, it will show you the command that it uses to compile, right? So that will have, you will see the -f OpenMP flag in it. Then we're going to try this with 16 threads, and we're going to run this, and then we can check if the answer is still correct. So the exact answer is 2.6667. That hasn't changed, but the dot product that we get is much less. But then it should at least be faster. Something's wrong, but it should be faster. We're running in parallel, but in fact, it's taking 0.5 seconds. So that's weird. It's 5 times slower and wrong. Clearly, this is not quite right. And even funnier is that if we run it again, we get the same sort of slowness, but we get a different answer. So whenever you run in a parallel program something identical and you get a different answer, chances are you're dealing with a race condition, right? So it's a wrong answer. The wrong answer is different every time, and it's slower. Like it couldn't be more horrible in terms of what we gained by doing this OpenMP. So this is a race condition. They can be very subtle because this one is very clear. There's no way that you're getting the right answer, but sometimes these kind of race conditions can give the right answer most of the time, and then sometimes it's not there. So it is something to be that can be tricky to debug. Sometimes it only happens, or you only see it when you scale up your size of your program. It's quite possible that if we did this for 10, a factor of 10 elements, we would not see it. And it's a problem with shared memory. It's a classic parallel bug. And the thing that's going wrong here is that we have multiple writers, multiple threads that are writing to the same shared resource. That resource is tots, right? So you can see it in the code. Let's go back. Here's the code. They are writing at the same time to the variable tots. You go, okay, that could be confusing, but I don't really care who does that first. As long as they all do it, I should get the right answer, shouldn't I? Like, how is this possible that this is wrong? Even if it's done in some sort of interleaved way, who cares? So the point is that it does matter. And the reason that it does matter is that that kind of a statement is actually not just one instruction or one thing that happens. And so we're gonna decompose that same statement of adding to a variable in a way that is closer to what actually is happening in the hardware. These days, nothing you program is anywhere close to what actually happens in the hardware. That's why you let your compilers optimize your code or in compilation. But this is closer and explains a little bit what goes wrong. So suppose we have a simpler case. Suppose our tot is 0 initially. We have 2 threads. One thread wants to add 1 to it. The other thread wants to add 2 to it. They should run in parallel. The answer should be 3, right? Because 0 plus 1 plus 2 is 3. But we could see any of the answers 1, 2, or 3, and the reason for that is as follows. When we do add a number to a variable that lives in memory, this is not one operation. It's not what is called one atomic indivisible operation. Rather, what can happen is the following. So say thread 0 is the one that wants to add 1 to tot, and thread 1 is the one that wants to add 2. It just so happens thread 0 gets to do this slightly like a clock cycle earlier. That what it does first, in fact, is to read the value of the current tot into one of its registers. So main memory is one thing, but every CPU, every core has some faster close-by memory where it stores things to do things with. So it first loads it into one of its what are called registers. So that's sort of local memory on the chip. What it does next is add 1, because that's what we want it to do, to its register, not to the actual variable. That might be the time. It's not quite cache. So we'll go through cache registers and things exactly in a moment. But imagine that it is cache. It isn't, but imagine. So it has its own register here. In that same time, thread 1 is starting its operation. So the first thing it's supposed to do is read the current value of tot into its register. Well, the current value of tot is still 0, right? Because I haven't changed anything. It's just moved into a register. The next line for thread 0 is to store its result into tot. So it stores 1 into tot. At the same time, thread 1 is adding 2 to its register. Very nice. And then the last thing that thread 1 has to do is store that. So in this order of operation, the result in tot that is stored in tot is 2. 1 was stored at some point, but then it was overwritten by the value of 2. So this is a case where we get 2. And depending on who gets where first and how these operations overlap, we could get 1, 2, or 3. If there was no overlap, if for some reason thread 1 was really delayed and doesn't start reading until this store of thread 0 has happened, then we get 3. We get the right answer, right? If thread 2 was the first one to get there, then thread 0 was the last one to get there, but that kind of means its value wins, and we would get 1. So the fact that there are separate registers and that these operations are not atomic, they're divisible and things happen in the meantime, is what causes these wrong results. Okay, so it's not just a matter of stepping on each other's toes, it's just wrong because some parts are not obtained. And in fact, if you look at the numbers, you do see the number is substantially lower that we get than what we should get. So that makes sense. We've sort of forgotten some parts exactly because of this kind of race condition. Okay, so it's wrong, but it's also 5 times slower, and that should be even more confusing. All these threads are running at the same time, and they're doing half or an eighth or however many threads I have less work, so they should be faster. And yet, no, that's not the case. So what's going on here? Well, tot is a shared variable. And so a shared variable lives in memory, right? Somewhere there's a value for it. And that memory is not the same as register. A register is a fast local bit of memory that every core has. It's private to the core in all senses. So it's not shared with the other cores. It can work on it without having to tell the other cores that they have changed. But because our variable tot is a shared variable, when it stores it, it has to store it back in main memory. Now, main memory is a lot slower than working in registers. That's why there is this difference. There isn't this idea of a Neumann machine that has a block of memory and then instructions that that act on that memory is not quite right. That's not really what's happening. That memory has a hierarchy. And so if we are working with a single core, what the compiler can do, or what really happens with the memory, is it can keep that what is it? It can keep all of the operations in registers. So it doesn't have to do the store here at the end if I have just one thread until it has added all of the numbers, and then it can then store it at the end. So every store is expensive. Every read is also expensive. But working in registries is slow. if I have 10 million operations to do, then for a single thread, I do all those 10 million as a fast operation in registry. Whereas if I do it in parallel, every one of these operations, every one of the 10 million operations has to write back to main memory. So even if it's just a little bit slower, we will see it. And in fact, we kind of see that working in register or working in main memory is like a 5 times difference. Okay, so it's even more complicated than that. So we have a layered or hierarchical memory. We have the cores here. Say there were 8 cores, for instance. There's some memory very close by. That's called, those are the registers. They're actually inside the core, really. And then on top of that, there is some sort of cache. The cache is there to help you get rid of this idea that memory access is slow. So what actually happens when you do a store from main memory to your register is that at first a part of memory, say we want this guy here, whatever that spot is, has to be loaded into core 3. It actually loads a whole bunch of its subsequent bytes into core 3 because a lot of the times you need more than 1 byte. So it reads a whole what's called a cache line into cache, so that you can load something, then you do a computation, and then you want the next element. It's already in cache. Cache is faster than main memory. So there's memory, there's cache, and then there's registers. Now, when you program, you don't have to know about these things per se, but when you tweak for performance or try to figure out if there's race conditions, you do have to know that, because the registers and also often some level of the cache are private to the core. And so this idea of having a true shared memory isn't true. And secondly, if I have to have shared memory, it has to go back to the main memory so that it can be shared among the cores. Now, modern architectures are yet more complicated, so it's in fact possible to have some layer of cache that is shared among the cores, and then some part that isn't. So you have level 1, 2, 3 caches, you have your registers, you have your main memory. But at the end of the day, the closer you get to this main memory, the slower things get. And a shared object is almost always slower to store and load again by another core than keeping things closer to your to the actual core. The caches, and that's one very big difference with the registers, are kept what is called coherent. So if I load an element here and I change it in cache, but not so in cache, so let's let that be here, then when core 2 tries to read that, it actually gets told, oh, this value has changed, so go update it. Update your own cache. And that's still somewhat more expensive than just keeping it as it was there, but that part is automatic. The registers are absolutely not coherent at all. And so this is all an optimization to get the most speed out of your computation, but a lot of this optimization happens without you knowing it when it's a serial code. All compilers are allowed to optimize out as much as they want, so that the serial code is still correct. But they do not know, they have no, it's too complex to figure out in a parallel case what they can and cannot do. So they just do it as if it's serial, and then it's your job to make sure that doesn't happen. So let's do that. Let's make sure this stuff does not happen. How do we fix this race condition? So there's a few things that OpenMP has that can help us here. The most sort of heavy-handed construct is the critical construct. What that does is basically say the next statement or block of statements should be done by one thread at a time. That makes it effectively atomic, right? But it does that sort of on a software level. So it puts in a lock to make sure the other threads can't access those instructions until the thread that happens to get there first was done. And so effectively, it serializes that region. So inside a parallel region, you can have a critical region that is not done in parallel, but by one thread at a time. So every thread does it, but one at a time. That way, there's never overlap between these instructions, and you don't get the wrong answers. So let's do that. So same code here, but before I do my update, I say this next statement is going to be critical, meaning only one thread does it at the same time. Here it is again. So we're going to run that again with 16 threads. And sure enough, we now get the correct answer. The only trouble here is that it takes 4 seconds now to do this. So this is what I mean with a heavy-handed way to fix things. It's 44 times slower than the serial version. So we have a parallel version. It is correct. The race condition has been fixed, but we haven't gained anything in terms of performance, which is really why we want to do this. So that is step number 1, making sure that it is correct. Can we fix this so that it actually is somewhat faster than the serial code? So the first thing to try is to realize that there's actually sort of a specialization of this construct, of this critical construct that's called atomic. And atomic is there because some parts of the CPU actually have instructions to make things atomic. So there's a difference between critical, which means only one thread is allowed to execute at a time, and atomic, which says only one, this instruction doesn't get split up. And so that is enough to get the right answer. If it's not split up, all of the instructions are done. And so we have, and that turns out that just updating a variable is one of those things that can just be done atomically. So we're doing it atomically. So if we do that, then we still get the right answer. Good. But it still takes faster. It's about twice faster than the critical construct, but it isn't. So what can be done with atomic are very simple things. So updates, adding to something, storing a new value in something. That's about it. Like if you want to compute, say, the sine of x, that's not an atomic operation. If you wanted to do some complex, anyway, it's kind of limited, but it works in cases like this where you simply add a value to a shared variable. Okay, so why was this slow still? Well, we haven't resolved the fact that we're still using tot as basically a main memory shared variable. So every time we do our update, we are updating tot, which means that we have to write to main memory or to some shared cache, which is still slower than registers, and we're still getting hurt. And we're getting hurt a lot now because we also have to make sure that things are atomic. So here's the solution. The serial case can forego writing to main memory because it can do its own sum in a register, right? The whole sum can be done in registers. But if we have a large array, we could have each thread sum up part of the array. It's what we're kind of doing anyway, but rather than summing it up into something that has to be stored in main memory, why don't we sum it up into a local variable, a private variable that can be kept in registers? So that's what's done here. So we tore apart parallel and for. So OpenMP parallel creates the threads. And now when the threads are created, they're all running the same stuff here. They each get their own local tot variable. Set it to 0 initially. Because it's defined here, it's private to the thread. So each thread has its own one. And then we do an OpenMP for loop where we're summing over x and y, but we're summing into local tot. And so the compiler now goes, oh, there's no reason to go back to main memory. All of this gets optimized to be in a register, just a register of one of the cores. Easy peasy, just as fast as if it was a serial code. And then at the end of these n loops, or n over the number of threads iterations, we do one atomic update to make the real tot know about the local tot. So this part is atomic, but it's not done n times. It's just done the number of times there is a thread. So if there are 16 threads, that's like 16 versus, what was it, 10 million. That's a lot less atomic operations. Most of it is done purely in parallel. So if we do that, we get the right answer. And now it was actually faster. It was about 6 times faster, 7 times faster. It's not quite 16 times faster. The reason for that is the same reason that our the last lecture's answer wasn't 16 times faster. It's because not only is there this memory system that is complex, it's separate from the GPUs, and you can kind of see. Let's look at the barrier again. If this is shared, there is some sort of maximum bandwidth from the memory to the cores, and that can be exhausted. So if the cores are asking for data too fast, then basically the memory is the bottleneck, and you're just not getting the data to the cores fast enough. At some point, you saturate that. Newer chips tend to be better, and in fact, if you look at what Marcella was talking about, Moore's law, which seems to be leveling off the fact that chips don't have not much higher clock frequencies than before. That's true. Those cores aren't getting much faster these days, but the memory system is still getting faster, which means that at the end of the day, they can feed these cores better and have better performance. Our teach cluster is somewhat older, and so that's so it feels that limit. So that's kind of what we're seeing here too. We really want those elements x, I, and yi very, very quickly. So by the time we have 16 threads, we've saturated that. You could play with this, see at what level of threads it sort of limits up. There's a question whether you can have different cores do different things at the same time. Yes, that is possible. You could either have a parallel loop that says I want a certain number of cores, and then another parallel loop that is in parallel of that. So nested parallelism, you could do it that way. You could do way more explicit things. You don't typically want to do that until you know there is a bottleneck like this. But you could have an if statement that asks if the thread number is a certain number, and if it is like less than 4, do this. If it's more bigger than 4, but it tends to have lead to code that is very particular to the number of threads you're running. Yeah. So yes, you can do a lot of things, but it's not always the best way, because you're really being very specific to the machine. Okay, so what we just did, this thing with local sums and stuff, is a little bit complicated, and it does not look like the serial code at all anymore. OpenMP actually has a way to do this with like one construct. Whenever you have a bunch of values and you have to add them up to one value, so you're reducing a bunch of values to one, that is what's called a reduction. So that's why this is an example of it. And what OpenMP has is a second type of, or third type of variable. We have private and shared variables. It also has what's called reduction variables. So what reduction variables do, and the example is easier, is they do all of this local summing for you. So a reduction variable is actually a variable that has local, has both private ones and shared ones. The private ones are used to compute, and then at the end of the compute, they are all, say, summed together to the shared variable that is the target. As I said, it's easier to see in action in a piece of code. So here's the code that does the same thing. And rather than saying that tot is a shared variable, I'm saying that tot is a reduction variable with the operator plus to be applied to the subresults of tot. So what that does is exactly the same as what we did by hand or manually, because it will actually create local tot variables in register, most likely, possibly in cache, but most likely in register, and add them up at the end with a plus operator. There's a few operators that make sense here. Plus makes sense, star makes sense, min makes sense, max makes sense. After that, it's pretty much nonsensical to do a reduction. You want reductions that are independent of the order in which you do them, right? But that's nice. OpenMP has that. We can run things, and we basically get the same answer at the same speed, but with much simpler code. In fact, this code is almost the same as our serial code, but we've just added OMP for default none, shared, and reduction. Also note that I forgot a parallel here. Sorry, so it should be pragma OMP parallel for. Sorry about that. So we can combine the parallel and the for again, and then have just everything done by specifying what the variables are supposed to do. Okay, so that's great. That's reduction. It's one way to reduce, in principle, dependent operations. adding to the same variable is a dependent operation that cannot be parallelized, to parallelize it nonetheless by under the hood changing the algorithm somewhat, but not in a visible way, not in a major way. Does this make sense? So this is a great way. We're leveling off at about 8 threads here, but if we had more threads, sorry, if we had more work to do per thread, we could probably get better speed up. So if we did do a sign here, which we now can do, we don't have to worry about whether it can be done atomically or not. Everything is done locally on the core. You would see the speed up be better because there's just more work per data element that has to be transferred to the chip, to the core. Okay, let's look at another case that comes up quite frequently as being difficult to parallelize. And those are the random numbers. So we saw in the random number lecture that what we create when we do pseudo-random numbers, or what we have the computer generate, is a stream of numbers. So we have some sort of state, usually it's kind of hidden, that you initialize with a seed, and then you advance that state through some sort of algorithm. Again, you rarely write the algorithm yourself, but there's something that advances the state from first state to second state, etc. And then we construct a random number from that state, such that it's either, say, uniformly distributed or normal distributed or whatever you have. So what that means is that if we want a bunch of random numbers, the nth number depends on knowing the n-1 number, right? So we have to have all the previous numbers, or at least the previous number, before we can do the next number. That's a dependence. If we wanted a loop that created, say, a million random numbers, we couldn't parallelize that, even though it would maybe look like it's parallelizable. It wouldn't be, because the random number generator is inherently serial. Right? This is the same kind of thing you would have when you have time-stepping algorithms. So when we have our ants, for instance, that are evolving in time, every time step needs the previous time step to start with. Before we have that, we can't compute. So we can't simultaneously compute 8 or 16 time steps ahead using each time step with a different thread. We can't do that because they're interdependent. So that sounds like we can't do this at all. We cannot parallelize random numbers. Anything doing random simulations, Monte Carlo simulations, anything like that should be stuck. It's too bad. That's not quite true. We can come up with a couple of ways to solve this. One is to keep one stream. So you just have one thread that creates the random numbers, and it feeds them to the other threads in some sort of way, or distributes them. Okay, so you could do that, but it turns out random number generation is fairly expensive. So it depends on how much work you want to do with those threads. When we want to do something like just adding two numbers or multiplying them, that is way simpler than the work that the random number generator has to do. And so what that can mean is that you basically have a serial code once again in terms of performance. You can also try to keep one stream, but try and see if it's possible to skip some numbers. So you could say, well, I want 1 million numbers, but I want it for, say, 8 threads. So why can't I have 125,000 numbers for one thread, and then the next thread just skips over those? Now, skipping over that is not necessarily always possible, because to skip over that, I would have to do all those intermediate ones. Some algorithms allow shortcuts in which you can make that skip ahead. And so you could use that in those cases. What the downside is there, that you have to know how many random numbers you are going to use in each thread at each step. So if 125,000 is not enough for that thread, you're going to go and overlap into the set of random numbers that is designed to be for the next thread. And so your independence of your numbers is gone. So that's not good. You can also do interleaving sometimes, which is a similar way, but means that you create, say, 16 random numbers by some clever tricks all at the same time. That's another way to do it. But none of these are very performant in most cases, and for some algorithms, for some random number generators, it's just not possible to do the skip ahead or anything like that. So what then? Well, if we remember that random numbers, the only thing we wanted for them to satisfy is that they're independent. We don't really care that there's one stream. Why don't we have separate random number streams per thread? All we want to know is that those random numbers are independent, so that I can't see any correlation between thread 0 and thread 1. If that's the case, then that's an equally valid way of doing my randomness. So there's a few things you can do to do that. But once you have a separate stream per thread, each thread is just computing their own random numbers. That's fine, but it only has to compute less random numbers than if it was a serial code, right? Because the work gets divided by the threads. So it's less work and it should be faster. So you have different seeds is one way. So remember, we need to give a seed to the random number generator. We can just have different seeds. We can do more fancy things where we give different parameters to each of the random number generators. That's more tricky, but can make them less dependent in a sense. We could accidentally pick the same seeds and get the same results for different threads. We could also have completely different kinds of RNGs. So there's different ways to vary things. I like to keep things simple most of the times and just have different seeds and pick a good random number generator. It's very important now that your random number generator is really independent, because you don't want correlations among threads to destroy things. And it is possible, if the random number generator is a bit unrandom, let's say, that say a seed 0 and a seed 1 have some sort of correlation. It's conceivable, right? It shouldn't be if it's well designed, but it could be. There's a question, if we change the seed, we won't have a Gaussian distribution, and that's not true. The seed is just to start the stream. From the stream, we can create, from each step in the stream, we can create a random normally distributed variable just by applying the same transformations as we would otherwise. So the distribution actually doesn't have to be changed in any sort of way. As long as we draw from the same distribution, and that's easy enough, it's safe. So it is not that easy to do, though. So I wanted to go through. A funny link happened here. Never mind the link. A funny thing can happen. So here's an example. It's not the best way to attack parallel random numbers, but it's also not the worst. This is a serial computation of the value of pi. It's actually based on the following observation. If I have a square table of size 1 by 1 meter, say, and in that I draw a circle with a radius of, I guess, a ½ meter, so a diameter of 1, and I start throwing random things on that table. If it's random enough, then the fraction by which they hit the circle, the inside of the circle, rather than anything else in the table, is pi over 4, just because the area of the circle is pi r squared, and r was a ½, right? So that makes sense, and that's what we're going to try and do here to compute pi. We're going to try 10,000 times or more times if you give a command line argument, so we can actually do more tries. And we're going to draw a uniform number between 0 and 1, and yet another one. So those are the x and y values on my table. See if they're within the unit circle, and if they are, then we count that. And then pi is 4 times the count divided by the tries. That's a Monte Carlo way to compute pi. It's horribly inefficient, but it does work, and it's a nice way to try and see how to parallelize random numbers. So the trick here is in the uniform, or the random numbers generation is hidden in the uniform function here. Here it is. This draws a single number, a double precision floating point between 0 and 1, and it does that by creating a Mersenne-Twister random number generator with a seed of 13, and then it has a distribution for real numbers from 0 to 1, and then, as we've seen, you just pass the random number generator into the dist distribution that produces a number, and you can return that. You might have noted, and I don't know if you guys have figured this out before, but that there's a static keyword in front of these variables. That actually turns out to be very important, because if every time I call the uniform function, it reinitializes my random number generator with a seed of 13, as well as the distribution, and then produces a random number, I get the same random number every time. So it's a random number, but it's the same one all the time, because I'm reinitializing the generator. What I want is that generator to stick around and to produce the next element in the next step. So static does that by a static variable inside of a function is a variable that is only initialized the first time you enter that function, and then it stays around. You can't use it outside of the function, but inside the function, when you enter it again, it's not reinitializing it to 13, so the 13 is sort of forgotten. It's whatever it was before the second time around. And so when I draw again, it now applies the transformation to the state, and the state is the one that was the previous state. So I get a new state, and so I get a new random number. So that's a way to do this. Another way is to go sort of object-oriented programming, create a class that saves the random number generator, and then pass the random number generator class to your uniform function. It's probably a more modular and better approach, but it's a little bit trickier to explain on a single slide. Note that yet another way would be to have these as global variables, but global variables are evil, so we don't want to do this. So this is sort of the intermediate between full object-oriented, okay, everything is local and stuff, and global variables, which are evil. It's sort of a global variable only when it comes to this one function. So it's encapsulated in that sense. So that's how this works. That's a random number generator. Each time I create a new one. Now I want to do this in parallel. The for loop looks very parallel. In fact, because all of the dependencies are hidden in the uniform case, even if we had a very clever compiler, they can see that there's nothing that depends on one another. It would miss the fact that there's dependencies in these static variables. So I'm giving the full solution here, but look at the int main first. That's the part that is the most straightforward. We're parallelizing our loop here, our loops over tries, so OMP parallel. We make tries shared, so we know how many tries we want, and count is a reduction variable because we are adding to the count. And Michael asks, if you're making a new RNG with the same seed each time, yes, you would get the same value every time. So the point of the static one here is that it is not creating a new RNG the second time it comes into this function. It's using the one that it already had before. So it's basically as if you had two return statements if you want. Okay, so the for loop seems totally fine. We've taken care of the obvious race condition in count by doing a reduction, so that is fine. And tries is just shared. By the way, shared memory is only slow really if you're writing to it, right? If it's just a read-only thing, it reads it once, and you get that slowness only once, and then it stores it somewhere in its own register, and it's fine, or its own cache. If you don't change tries, shared is fine. Read-only shared variables are very fast because the memory system does its caching for you. Okay, so let's look at what we had to do to uniform to make this work. So I did some bad global variables. I'm doing it anyway because otherwise it's hard to explain. That are going to be additional random numbers to randomly create seeds. So my seed was 13 initially. Now I'm going to draw seeds for each thread randomly from yet another distribution. What kind of distribution should I have? Well, seeds are integers. They actually turn out to be unsigned integers. So I have a uniform int distribution from 0 to the maximum uint that is possible. This one is defined in the climits header. That's why that one is there. So these ones are initialized just at the start of the program. And then the uniform function does something similar to before, where it creates a random number generator of the Mersenne twister type, but it generates it with a random seed. I see I have a bracket missing here, but a random seed that it gets from this global random number generator. Then it uses a distribution and it does the same. But what I want is for each of these to be specific to the thread, but still sort of static. So there is a keyword in C++, actually C++11, it's called thread local, that does exactly that. So it is like static, where these are initialized only once, but only once per thread. When the same thread calls the uniform function again, it reuses that already existing object. It doesn't reinitialize that. But if another thread comes in and it hasn't initialized this yet, it initializes the random number. So this is the sort of the equivalent of having a private in an OpenMP parallel, right? But it's private per thread, but still static as far as the function is concerned. So every re-entry of the function does not reinitialize these values. So just to cover this and make this clear, static is a keyword that comes originally from C. It has too many different meanings in C++, if you ask me, and they're very confusing. The way we've used it is for a variable inside a function or an object declared in a function that only gets initialized the first time you call the function. Okay? You can do other things that I won't discuss here, but I've mentioned here just in case you've heard of other uses of the static keyword, but this is the one we were using. That doesn't work in a threaded environment because, first of all, threads might be trying to initialize the same static variable at the same time. So that's a race condition in and of itself. Calling a function that has a static variable is in itself a race condition if you do it in a threaded environment. And you don't get a private version for each thread. So that's why C++11 created the thread local keyword. And it does the same as static, except every thread initializes its own static variable. It also has meanings for the other meanings of static, but that's what we're using it for here. Okay. So it's very similar to OpenMP's private. There is also an OpenMP pragma that can sort of do that, but it's not as powerful as the C++ thread local keyword. So we're doing it this way. Okay. Does this make sense? So every thread is creating its own random number generator with a seed that is created from yet another global random number generator. And after that, each uniform it's almost like there is a uniform function per thread. You could code it that way, but that's a horrible way to do it. This is a nicer way to do it. And so as far as usage, it looks like we're just parallelizing a loop and don't even care about the interdependence. But there's still a race condition here. So anybody have an idea why there's still a race condition when I set up the random numbers this way? This race condition is trickier because you might not always see it. And in fact, when it comes to random numbers, it is really tricky to see it. You might have to print out the actual numbers and see correlations before you know that something is wrong, because the estimate of pi won't be far off, and it's random anyway, so you don't know what it should be. No? No ideas? So the race condition that's left is in the creation of these local objects, because they all call sdist at the same time. Possibly. It depends on exactly when each thread calls uniform the first time. Let's say they all do it at the same time. Then I've got, say, 16 threads all calling the sdist function at the same time. So they are going to try and update the current state all at the same time. And who knows what happens there, right? So we will need to fix that to make it truly what is called thread safe, so safe to use within threads. We could go very heavy-handed and just say, well, Whenever you call uniform, only one thread can call it at the same time. But then we're serializing our uniform random number generation, right? So that's not very good if we do it every time we call uniform. But we could do a little bit what we did with the reduction and only call it the first, only try and stop things when it really matters. So it really only matters in the initialization. And that makes the code a little trickier. Here's one example, tricky enough not to fit on the slide, but you have to trust me. The in main was unchanged. So I now have to only do a critical to initialize the random number generator, right? And that is tricky because it turns out I can't do a OpenMP parallel on a variable declaration. When I do that, when I try that, this actually becomes a local variable to a block of code, and I can no longer use RNG outside of it. So that's not good. So I have to do this two-step thing. We've seen it with the opening of functions too. So you can actually define an object without initializing it, and then initializing it later. So one way to do it is in this case, just say RNG, and then we initialize by hand with a certain seed the RNG, and that seed is randomly called. So now for that to work properly, I have to have a way to know whether this was the first time I go into this function. And so that's to do that, I create yet another variable called uninitialized that becomes true the first time you go in for each thread separately. So this is my flag that says, is this the first time I came in here with this thread? And if it is, then it's true. And if it is, then it will initialize the random number generator in a critical section. So each thread only does it one at a time. So there's no race condition. But it only does that when it's not initialized. And then it says uninitialized to false. So the next time that thread goes through here, it just reuses the RNG that is already initialized here. It doesn't have to do this. It skips that, and it just does the distribution. It's tricky, right? What's nice, once you have done this, you probably put this in a module and go, great. And then the way you use it, you hardly have to know that this is true, but you should somewhere have specified that uniform is a thread safe random number generator, because you can't really know that for sure. When you're using random number generators that you found somewhere in a library, you should look up whether or not they are thread safe. And they can be thread safe in two ways. One is be very safe and basically have the whole thing always be OMP critical, but then they serialize all calls to that function. So it's safe, but it's not very, very fast. Another way is that they actually do try to do these kind of tricks to make sure that they can run in parallel as much as possible, but where it matters, where it's critical, they do not step on each other's toes. Okay. Does it make sense a little bit? Yes, that's a lot of code for Pi. Sure, we'll go through it one more time. I don't mind. So let's do it line by line and see if we get that, because that's kind of how the compiler looks at it too. Obviously, you have our I/O routines, random C-limit. I don't usually do using namespace std because everything gets into the namespace, but it keeps this a little bit more understandable. Here's a creation of a random number generator of the Mersenne twistor type. Its name is sRNG, and it gets initialized with a seed of 13. There are ways to make that not so hard-coded either, but let's just say that this is okay. And I want to use it to create a uniform seed. Seeds are integers, so here's the distribution to get a uniform seed. And it can be any integer from 0 to the max of unsigned integers. Happens to be this variable. So with these, I can draw anywhere in the code. I could draw a number between 0 and uint max that is random. I'm going to do that in double uniform. So double uniform is a function. It will get called by different threads at roughly the same time. And it needs some way to have a different version of its variables, so private versions of its variables. And that's why these things are all thread local. So each thread will have its own uninitialized variable inside the uniform function, its own RNG inside of the uniform function, and its own uniform real distribution. This one's probably not so essential to be there as thread local, but that's okay. But I have to initialize these things the first time I go through the uniform. So to be able to do that, that's why there is an initialized variable for each thread. So the first time a thread comes in here, it sees that all of the things are uninitialized because the value of uninitialized is true. It also defines an uninitialized RNG and a properly initialized dist. And then if it's uninitialized, so that happens the first time it goes through it, it critically calls the seed setting function of its random number generator. So that one has to call our global random number generator and therefore has to be critical because several threads could be doing this at the same time. And then very critical for the operations of this is that I set uninitialized to false after that. So that is, this thread now signifies basically to itself that the next time it calls this function, it doesn't have to do this again because uninitialized is only set to true the first time it goes through this function. Okay. So after this, we know that RNG has been initialized for sure. It is either the first time around or not. If it's the first time around, it gives the first random number. If it's the second time around, it gives the next random numbers, the third time, next, etc. Okay, does that make sense? A little bit? Oh, because int should have been bool. That's a typo. Yes, this int here should be bool. That's a good question. It does work. Turns out you can convert bools to integers, but it shouldn't work. So this is just incorrect. It should be a bool. So this seems like a lot of code for computing pi. It's not that much code for doing thread safe performance random number generation. So when you're going to need random numbers that are independent and for different streams, you're going to reuse something along these lines. Would it be bad to just make the seed the thread number? No, not necessarily. That is probably fine. The thing is that you would now have to investigate that, right? And you'd get, yeah, that's probably fine to just say instead of as this, say OMP thread num and use that is probably okay. But I'd like to see a test of that to see that there is indeed no gross dependencies. Because as I said, if there's going to be dependencies between different seeds, just naively, it might not even be true, but I would expect that like seed 1 and seed 2 are more correlated than seed 1 and some random number. If there's any correlations between the seeds, then if I choose them regularly, there's a good chance I will pick up those interdependencies. But if I choose them randomly, then even if there's sometimes correlations, the chance that I get them are lower. So it's a safer way to do it. It's more random, more likely to be okay. In all of these cases, by the way, if you're ever doing Monte Carlo simulations or random things, you want to run things a few times. So you want to at least try this and vary the sort of the master seed here, the 13. If 13 gives the same as, I don't know, 255, and it gives the same statistically the same result as say 1,000, then things seem to be in order. If they give wildly different results, you got to investigate your random numbers. I had a third section, which obviously we're going to skip, on what to do when you have for loops, where what you do in each loop is not always the same computational load. So I equals 0 might be less work to do than I equals 1. And why that matters is that the default pragma OpenMP4 divides the iterations equally over the threads, but it doesn't know how computationally heavy each iteration is. So it could happen that thread 0 gets all the heavy lifting iterations and has to do a lot of work, and the other threads aren't doing much at all. So they're just sitting idle, saying, we're already ready with our batch. I don't know what's keeping you so long, thread 0, because the iterations are unbalanced. So to do that, there are a whole bunch of load balancing techniques. And so I encourage you to read through that yourself. And you would see that you have a load balance situation when you do your performance analysis and you see your code that is using 8 threads is only running at 200% CPU or something. So there's CPUs left idle. That's when you want this. I think we won't use this in the assignment, so it's kind of safe to skip over it. But there's some fun parts here, pretty pictures too. So I'm going to leave it at that because so what we have seen mainly is to deal with two kinds of dependent calculations. One was a reduction where the dependencies could basically be put to the end. The other was random numbers where the dependencies shouldn't be there. The whole point of random numbers is that they are independent or seem independent. And so the dependencies was sort of an artifact. And so we found a way to get around that by having independent streams. If you have true dependencies like time stepping, I already mentioned, there's no hope. Like you cannot parallelize in the time dimension in those cases. There might be a grid of X values, right? A spatial grid in which you can parallelize, you can do things in parallel, but the time step is sort of stuck. Yeah. We will, a few announcements, we'll also email them. We will set an assignment, I think we'll set it today. I'm trying to get back to a Thursday schedule if we can. We haven't entirely fleshed out what it will be, so sometime this evening probably we will post it. But keep an eye out on that. It's going to be about OpenMP. We're going to do some parallel programming, so that should be fun. The other warning I should say is that we're going to migrate the education site from its current server to a new server. The new server is much better, but in that migration process, it'll be off. It'll be unreachable for about half an hour, starting probably at 9 a.m. in the morning. So if you have some trouble tomorrow, somewhere in the morning to connect, if you're trying to connect, that is probably why. We have a backup plan. If something goes wrong, we just revert to the old server for now. So it won't be off for the whole weekend in whatever happens. But I expect this to be a fairly quick process, but you never know with these things. So there'll be some downtime of the education side around 9 a.m. tomorrow morning. Any other questions? Yes, so we can do that. If there's a real problem, we can email the assignment info. That's fine. Yes, that's not a bad idea. Berang asks, how is critical limited? I'm not quite sure if I understand the question. Do you mean how does it work? And how does it make sure that the
I guess you said it's limited due to the hardware structure at some point.
Oh no, that is no, that's not critical. That is the atomic. So atomic and critical seem to do the same thing, and they do at a high level. But atomic, so critical just says this piece of code can only be done by one thread at the same time, and the OpenMP compiler and runtime, because it has to check that as it's running, can do that for you. Like there's no issue. It's not limited. You can do critical for any piece of code. but it has to do it by basically checking if any other thread is using that piece of code at that time, right? So that there's mechanisms called locks that it would use for that, and it all does it for you. That is great, but those mean that your code is serialized, and even setting those locks is not cheap. So that's what it is limited. It's limited in terms of performance. Atomic is less limited in terms of performance, but it relies on the hardware of the chip being able to do, say, those steps that I had, where you load the value, you add a number to it, and you store it again. Those three subdivisions of that statement can be done as one statement, and as one true CPU statement, and that's an atomic statement. But not every combination of statements can be converted into atomic operation, because that actually has to be some hardware in the chip that can do that. So that's why it's limited. Most chips now can do things like updating a variable, or reading an old value of variable, or adding to a variable, something like that. They can do that atomically, but after that, it's pretty much done. So it's limited in the number of operations, or the kind of operations they can do in an atomic construct.
Thank you so much.
No problem.